We're now going to look at how often molecules collide with one another. And in order to get a handle on this, to maybe help you gather some intuition about this, I want to propose an analogy. Imagine if you're walking down the street in a busy downtown area like New York City, or it could be downtown San Antonio, but there are fewer pedestrians in San Antonio. But I want you to measure that you're walking down the sidewalk and there's lots of pedestrians, and let's say that all of them are blindfolded. Well, you can imagine that you would be running into quite a few of them because you're all blindfolded and you can't see where you're going. And molecules are like that too because they're blindfolded. They don't have eyes, they can't see each other. But what factors would cause you to run into people more often? Well, I think it's pretty easy to come up with a small list. I mean, one, your size. If you're large, you're going to run into more people. If you're small, you'll run into fewer people. Your speed. If you're fast, you're going to run into more people just because you're running down the sidewalk, and other people will happen to be there and you'll run into them. So there's a couple of things that are going to really affect how quickly or how frequently you're going to run into other people. And the same is true of molecules. So what I want you to imagine is we've got some molecule. I'm just going to draw, this is a really poor molecule. This molecule doesn't seem to have any atoms, but it does have a shape of some kind. And now I'm going to specify that the dimensions of this molecule or that it has some sort of width that I'll call d. You can think of that as a diameter. So the question is, how can I begin to build, if you will, a model that will depict how this molecule is going to run into other molecules? Well, the first thing I might do, and I'm going to have to redraw this molecule, I'm afraid, but it won't be an exact replica. Okay, here's my molecule again with its width d, and there's going to be some sort of radius about this molecule that will represent any time a molecule comes within this radius, we can consider that to be a collision. All right, so how big would that be? That'd be kind of a big circle. But if this has a width of d, what I want to convince you is that the radius of this circle will be roughly d. In other words, if the centers of two of the same molecule come within that distance of one another, we can consider that to be a collision. All right, so in this case, our molecule here is going to have a collision within this area, which I can describe as pi d squared, as sort of the area of this region. But we know that molecules don't exist on a plane. They exist in three-dimensional space, and in fact, they're moving in three-dimensional space. So what if I were to take this molecule and now think about it moving? So here's my molecule again, poorly drawn. And I'm going to draw an edge on this circle that's around it that represents this distance d. Now, rather than go with a circle, I mean, it doesn't have to be a circle. It can be any old area. I'm just going to say that the area of this thing, this region here, is something called sigma, and we'll call that the cross-section area of the molecule. So it's the cross-section that needs to be invaded by another molecule in order for there to be some kind of collision here. All right, now if this molecule is moving through space in this direction, we can think of this cross-section, sigma, as sort of mapping out some volume, okay? So you can imagine just moving that circle through space as this molecule moves, and it's sweeping out some volume here. And this volume is going to be essentially going to be the area of the cap, the sigma, which is the area of the cap, times the length here. Okay, but can we do something that would tell us what that length is? Well, let's think about it. Okay, we've just spent last time deriving what the average velocity was, and I'll remind you that it was 8 kbt divided by pi m. So we have a nice value that we can use that tells us how fast the molecule is moving. Well, how fast it's moving and the amount of time that it's moving, I'll call that delta t, that would basically give us this length. So this length is going to be the average velocity times some length of time t, delta t. So the whole thing here, this volume that is being mapped out by this molecule, is essentially going to be the cross-sectional area, sigma, times the average velocity times this time delta t. Okay, good. Well, so what? Well, we know that this isn't the only molecule in the world, and in fact, if you're on the street in New York City, you're not the only person on the street. So there's going to be other molecules around you too, and those other molecules are going to exist with a certain density. And so for this purpose, it's useful to define something called the number density, which is basically the number of molecules per unit volume. So take the total number of molecules in the system divided by the total volume of the system. It'll be equal to n over v, and we give this the convenient symbol rho. All right. So if we have this, that means that whatever the size of this volume is, the chances there's going to be a molecule in there is given by rho. Or in fact, there will be rho molecules in there if we multiply rho times this volume. So now I can say that, okay, the number of collisions that I'm going to undertake in this case is going to be rho times sigma times the average velocity times this change in temperature, change in time rather. All right, so we're getting closer now to understanding how many collisions this molecule can undergo. And in fact, we are almost to where we need to be. What I want to define is one further thing, and we don't really want to specify a particular time interval here. And it's not really the number of collisions we're interested in so much as it is the rate of collisions. So what we're going to do is define one other quantity, and that's the rate of collisions that this molecule, this one individual molecule, is going to undergo. And it's going to be the number of collisions over some period of time. And we'll just use that same period of time to get that. So for this rate now, I can simply write it as rho times sigma times the average velocity of these molecules. Oh, and now we're getting a fairly simple picture for how this looks. And in fact, if I were to simply plug in the value for the average velocity, I could write this as rho times sigma times 8 kBt over pi times m. And this is all raised to the 1/2 power. All right, so this is, in fact, the result that we're trying to get to in this. And I'm going to write that as z collision, which is basically the collision rate for a given molecule, okay, which has this average velocity. Now, I've really kind of shortcutted this process a little bit because I've treated this as though there's only one molecule moving, right? This target molecule here in the middle. Okay, but in fact there's lots of molecules. In fact, all of the molecules are moving. So what we have to do is we have to account for the fact that some of the molecules are moving toward this molecule and some are moving away. Some of them are moving in a direction that's perpendicular to this. So in order to make that change, you need to do a little bit of statistics. It's not impossible to do, but I don't really want to dwell on the statistics so much as I want to get to the final result. And the basic idea is that we're going to take our mass that appears here in this result, and we're going to exchange it for something called the reduced mass. This is the way we can account for these other molecules moving. The reduced mass is simply going to be the product of the two masses of the particles divided by their sum. And if these two particles are the same, I think it's pretty easy to convince yourself that we're just talking about m over 2. So since that's in the under the square root sign for this particular expression, that means we can write a final expression for our collision rate that now takes into account the fact that we have molecules that are moving relative to one another, so that would be a relative velocity, and now it has square root of 2 in front of the rho times sigma times the average velocity of these molecules. And with this average collision rate, we'll actually be able to begin to put together some further interesting facts and figures about this system and learn a little bit more about its tendency to undergo reactions.